Hello world, and welcome to Foundations of Algorithms.
Hannah here.
My name is Koya.
This is Liam.
My name is Alex.
My name's Isabel.
My name's Lenny.
I'm Stella.
My name's Alec.
I'm Thomas.
Welcome to Cont 2002.
Welcome to Foundation of Algorithms.
Welcome to Foundations of Algorithms.
Welcome to Foundations of Algorithms for 2022.
I hope you all have an awesome semester.
Looking forward to see you guys either online or in person.
We're always here to help.
Algorithms are fun.
Algorithms are fun.
Algorithms are fun.
See you soon.
Hi everyone, and welcome to Foundations of Algorithms, the class that will teach you how to analyze and solve problems using algorithmic thinking. Hopefully you've already attained some basic competency in programming, either by completing the programming competency test or through Foundations of Computing. But now here's your chance to really get your hands dirty, to understand not just how to program, but what the right way to think about a problem is. Throughout the semester, you're going to learn how to approach different tasks, how to break them down into their components, how to analyze them, and then, yes, ultimately, how to solve them. We have over 450 students coming from 6-degree programs and all over the world. These are your 9 tutors. Hopefully you'll meet them soon when our workshops begin in week 2. I am also not the only person involved in the class other than the tutors. I want to invite Dr. Zhang Zhong to come and introduce himself to all of you.
Hello everyone, my name is Zhang Zhong. I'm teaching with Dr. Shannon together for the semester, and I hope you guys all together enjoy this semester. Thank you guys. By the way, I'll be reachable through Tuesday consultation sections online in Zoom. If you turn on the Zoom page in our subject canvas site. If you want to meet me in person, email me, we can book appointments. Thank you all. Enjoy.
And on that note, I am going to ask a bit of patience from all of you this semester. Running the in-person lecture while half of you are online is going to be a considerably complex task, and the university is still in the process of working out exactly how this is going to function. So please excuse any small technical hiccups along the way, and approach the class with a big smile on your faces. So as you've no doubt discovered, hopefully over the last week, the LMS, which is still an evolving page, but I trust you've enjoyed the fairly clear layout that we've set there for you. On the LMS, you'll find all the information you actually need to complete this class laid out very helpfully and in detailed syllabus. And we'll cover some of the key highlights today. I encourage all of you to go and take a read of it fairly closely to understand some of the more subtle elements that I don't have time to cover today. But it's not only the technical elements of this class that are evolving, but some of the course policies as well that we'll need to adjust as the situation changes on the ground and as we become adjusted to this teaching mode. On that note, announcements for this course will not actually be made on the LMS this semester. We're going to try and use the EdSTEM platform and the interactive Q&A platform that many of you can access via the LMS. So that will replace the chat and the announcement functions. We'll probably do a brief tour of the LMS maybe in the next lecture to show you how to access some of these features. For now, don't worry about it and just sit tight and enjoy your first day. This here is one of my role models. His name is David Malin, and he teaches the Introduction to Computer Science course at Harvard in a course named CS50. One of the key principles by which he runs his course is the idea that success is not the grade you attain at the end of the year, it's not whether you get an H1, it's ultimately where you stand relative to yourself today. If you come in knowing a few algorithms already, by the end you should have a new level of mastery. If you came in today not knowing a thing at all, hopefully by the end of semester you'll have gained a new appreciation for algorithms as well as some new skills and some knowledge about them. Your task is not to beat everyone in the class, but to beat yourself today where you stand now. And if you walk out of this class at the end of semester knowing how to do a few new things and having an appreciation for the subject, you've won. We're studying algorithmics and algorithms, so let's kick off with a case study that shows us why we're bothering. I mean, you already know how to program, so what more is there? Why are we still here? And why am I not just exiting stage left and leaving you all to go to industry? Well, as it turns out, the art of writing a program well is not the same as just writing functioning code. Furthermore, computers are finite. They only have so much memory and so much speed, and we only have so much time. If it were the case that we had an infinite computer as big as we wanted with infinite time, well, I guess we wouldn't have this course. You could write code that you liked, and as long as it eventually solved your problem, I guess you'd be okay. However, our real computers are frustratingly finite. I'm sure many of you have been irritated at times when your computer's running slowly, when it's not completing the things you asked for and it's taking a really long time, when you get those strange out-of-memory errors that perhaps occur when you've opened like 30 tabs on your computer, and suddenly everything slows down. What we're going to learn is how to find solutions to classes of problems that change the amount of resources those problems consume, allowing us to solve very large problems with finite amounts of space and finite amounts of time. So let's take a little trip down history lane in order to find a problem that can help us concretely understand what's at stake here. Yes, this is in fact the Enigma machine developed in World War II. This was the Nazi code machine. So before we had modern computers and modern cryptography, the field that I study, we had mechanical cryptography and cipher machines. The way it would work is you'd have a complex configuration of different dials and different wheel settings and different plugs that you plug in the front of the machine, and according to how you set this all up, it would determine what outputs you'd get from the machine for what inputs. In order to decode a message that was created using this configuration, you'd have to know the exact same combination of plugs and settings as the person who sent you a message. So if you're enciphering a message, when you press a button, another button at the top would light up showing perhaps if you enter the letter S, the letter L would light up, and you'd know that's the letter you write down and send to your friend. Likewise to decode. So the Germans hid many of their communications using this machine, and this caused a problem for the Allies because without good intelligence, they were blind to the many movements of the German troops. And so thanks to the brave efforts of some Polish cryptanalysts and Alan Turing, a famous British cryptanalyst and computer scientist, the Allies were eventually able to break the Enigma Cipher and win World War II. But before we get to more of that exciting story, we are going to cover a little bit of the syllabus and a little bit of information about our course. So this part of the presentation is going to mention how to be successful in Foundations of Algorithms, and I have a few notes that I'm going to pull up on some small course material that I'd otherwise struggle to remember. So firstly, given that we're still in the middle of the pandemic, I want to assure you that you're welcome to take whatever precautions that you find necessary, whether this means wearing a mask in your in-person tutorials or attending or online instead of in person, and particularly if you're sick, please don't come to class. We all have wonderful facilities and tutors that are all available online and that are going to ensure you get as an exceptional an experience as possible while you're in recovery. The university also has policies around what to do if you get sick, a notification system, but it's incumbent on each and every one of us to keep all of us safe and all of us healthy. So please respect whatever precautions everyone's taking, but if you're sick, do the right thing and stay home. There's also a tutorial each week that'll be recorded, so if you're more sick than sick and are unable to even attend your online tutor, there's going to be a recording after the fact. So one of the things, an expectation that I want to set this year is if you're attending an online tutorial or online lecture, if you're not watching something pre-recorded, please leave your camera on. This is a community norm, so we're not forcing it. However, if you wish not to abide by this norm, please just send me an email with a small note. It can be a one-line saying, you know, I'd rather not have my camera on, but otherwise the community expectation is that your camera shows us that you're there, that you're participating, and that you're fully engaged. This will help us to ensure a good experience not just for you, but for all of your classmates. Well, moving on to some of what we expect from you in terms of the actual substance of the course. We want you to regularly check Canvas and also to check Ed. These are the two platforms through which we will be conducting the majority of class activities. The LMS will serve as the de facto class webpage, while Ed will serve as the announcements platform and as a home for questions and answers. In a first this semester, the entire code for the LMS is actually available on GitHub. So if you find a mistake on the LMS and you feel a bit adventurous, feel free to submit a change request, a pull request via GitHub. And you could be the next person to have your name added as a contributor on the class website. Number two is that we actually expect that you do attend class. So I'll do my very best to make the lectures as exciting, as adventurous, and as participatory as possible. We're going to have 3 of them per week, as well as your tutorial sessions that are going to begin in week 2. And the tutorial sessions are going to be structured as follows. So 40 minutes to an hour of discussion of the material covered in lecture to help solidify your understanding of some of the concepts. And then in the second hour, it's an opportunity for you to practice. We have a whole lot of activities designed for you to pace your way through. And in another first this year, we're actually making the complete set of the semester's activities available from day one. This means that as soon as you're ready and at your own pace, you're going to be able to go through these activities and build your skills. Building your skills is important because the design of and art of algorithms is not just theory. It's something you're going to attain through practice. And if you don't practice and develop your skills, ultimately, at the end of the day, you're not going to achieve your potential. Carrying on from that discussion, we do have some expectations around the amount of work that it'll actually take. It's estimated by us and by the university that for every contact hour that you have, it's going to take around 3 additional hours of your own work to succeed. This work will take a variety of different forms. It could look like lecture prep, it could look like the readings, or doing some of the coding exercises. Also, in terms of the book, we follow it relatively closely, if not in identical order, so I highly recommend that you source a copy of it, whether online or in person. And this is actually one of the very important things that I want to stress for class next, is to ask for help. And I mean this in a variety of ways. So the first way will be a little more obvious. It's when you have a problem, post a question to Ed. If you get stuck, it's worth spending a little time trying to solve it yourself. But if you have come to a point where you're blocked and you've Googled it and you've tried again, and if none of that works, we're here for you as a resource. That includes both your tutors and Junjong and I, who are always happy to answer questions. And if at all possible, you should not make your questions on Ed private. Why do we ask this? Well, it's so that everyone can learn from the questions that you have and that you can learn from others. However, when we say ask for help, we also mean it in a bit of a different way. So we're aware that all of you are not just students in Foundations of Algorithms. You're of course people, and as people, we're all living through a very tumultuous period in history. Whether that be the very difficult to watch circumstances stemming from Russia's invasion in Ukraine, or other geopolitical situations, or the pandemic that surrounds us, that surrounds all of us. And we understand that sometimes life gets in the way. So if at all possible, before a situation arises or when it's on the horizon, reach out to us and let us know your circumstances, and we'll find ways to help ensure your success in the class. If you do come to us after an assessment that's already been handed in and after it's graded, it's often too late for us to do anything. So we request that you come to us even if you think that something might be a problem. Come to your tutor or come to me and Janjong. Come with your problems early and we'll help guide you through. Ultimately, what we care about is not the rules in the handbook, although they are important. What we care about is your success and your well-being. Another note on this is that many people have, and I can even say for myself, throughout life, we have different life circumstances that can involve physical health struggles or mental health struggles. And while none of your staff members are trained counsellors, and if you have a real issue, we encourage you to visit your mental health professional or doctor, we are here to lend an ear if you feel that we're the ones that you can turn to, and we are. Know that if you're ever feeling alone or lost at the university, my door is always open, and I'm sure that the rest of the staff members would always be happy to help you find support, and we can be another person in your life who you can touch base with and get some guidance to help you along. Another important element of this class as it evolves and as it changes is your feedback. While we pay very close attention to the end of student semester surveys, which giving us feedback earlier in the semester allows us to adapt the course to make it better fit your needs while it's running, whether that's elements of the technical delivery or setup, or if there's something that isn't working, let us know. Maybe there's a course policy that you think should be a little different. Let us know if you think there's something in the substance that should either really be there or really not be there. The message is the same. Student feedback is important and we do listen to it. That said, we won't always agree, and that's okay. Education is difficult and the research in the field is growing, and often there aren't really correct answers. However, we'll listen to you, and by doing so, we'll make informed decisions about course policies, design, and structure, and we can all help to make Foundations of Algorithms better. Not just for you and your class, but for all the classes that come in the future. So turning to a slightly more difficult subject, this is the one of academic honesty and academic integrity. Traditionally, first-year computing subjects have had a little bit of a problem with academic integrity, and so we wanted to dissuade you before it gets to that point, before you commit the same mistakes as some students have committed in previous semesters. We do want you to be able to attend, to turn to your peers for help and get support online. However, beware stepping over the line. Misrepresenting others' work as your own, whether that be from Google or from your peers, sharing code too closely, or doing things like that can really be a problem and put your future in jeopardy. And we'll discuss this a little more as we get further in semester. The academic integrity expectations of the university and CIS are paramount, not only to the integrity of the degree in some abstract sense, but to your individual learning and for our bond between each and every one of you and me as your instructor. I really can't help you if you don't be honest with yourself, if you don't put in the work yourself, and if you don't come to me when you're struggling instead of engaging in other practices. And on that matter, we do have pretty sophisticated systems, including algorithms that are designed to detect when you're engaged in violations of the academic integrity policy. So while it may seem like a good idea the night before an assignment is due to copy a bit from Google or ask a friend for too much help, we can often detect this, even if you change your code around to make it look different. And I'm not denying the importance of grades to your happiness and flourishing, but the grades are only a means to an end. The goal isn't to get an H1 to get an H1. The goal is to learn something. And because we're aware of that fact, we do have assessment tasks, but they're structured so that throughout the semester you'll be engaged in constant learning and finding how to improve your skills. So starting with the mid-semester test halfway into semester, this will account for about 10%, conducted using one of our online learning platforms. We're still figuring out the exact details, we've got some fun ideas, and we'll let you know more closer to the date. We also have 2 assignments that'll really test your programming mettle. These are worth a combined 30% due in weeks 8 and 12, tentatively, and then finally a 60% exam at the end of semester, which will test some of your abilities to code under trickier situations than you'd find at your day job in industry. However, even in the real world, you're not always going to have a computer around, because to become a real programmer, you often have to perform programming interviews. And these will be a little more similar to our final exam. You'll be in a room with an engineer standing next to you saying, "Tell me, Mr. or Mrs., if you have seven beans in a bag and you have 3 green ones and 2 blue ones, write me some code that'll simulate the probability of drawing any given combination and produce a graph of the likelihood of each draw." And you'll be standing there with a whiteboard marker in your hand and with the whiteboard next to you, and no ability to turn to books, and no ability to turn to Google. So it's actually quite important for your professional development that we do conduct some of these style exams, and we're always looking for ways to improve it. So if you have questions for next year's cohort, whisper them in my ear, and we can see if we can put them in. However, to pass this course, we do have combined hurdles that ensure you've gained both the more theoretical skills, and like the interviewing skills, and also the general programming skills. So we require a 28 out of 70 combined on all the test components, along with 12 out of 30 in the projects. Now you'll note that neither of these are actually 50%. These are just hurdle requirements where you show that you're meeting a minimum benchmark in both components, a minimum on the tests and a minimum in the projects. As long as you can do better enough in one of them and attain 50% overall, you will pass. Now onto what you should be doing week 1. Well, start reading the textbook. We've already put some readings up on the LMS. Some of them we'll cover later in the week, but we're going to be a little bit flexible on pacing, so even if the exact materials that you read aren't covered the day you expect it to be, it will ultimately be relevant to the class. Another thing to note is that we're not going to touch every single point in the book during the lectures, but they're still part of the course, because there just isn't enough time for us to go through the book with a fine-tooth comb. So by reading the book, you'll come away a stronger student than you would just by watching the lectures. And this might mean reading it very closely, it might mean skimming it a little, but we highly, highly encourage you to at least, at minimum, take a flip through it. The other important thing that you need to be doing is getting ready to have fun. This class is meant to be really enjoyable, the projects are meant to give you inspiration, the lecture's super engaging, and so if you're not having fun, we're probably doing our jobs a little bit wrong, and then it's time to go back to our point about feedback. One other note on the slides. Well, contrary to the way that many lecturers teach, my slides are actually not designed to be your revision materials. And yes, I understand that this might be a little bit frustrating for some of you who are used to using the slides as your study aids. So I will post the slides that are used in the other semester that function a little more like revision materials. But in order to communicate with you better, the type of slides that I use are a bit more minimalist and will actually be, I think, more effective in helping you to grasp the material covered during lecture. I believe it ultimately provides a better educational experience. And because I make these so close to the lecture, they probably won't be available until right after. Let's cut back to our story.
In post-World War I Europe, secrecy between paranoid nations becomes paramount. The growth of international commerce creates a need for companies to keep their information secret from competitors. Germany's Arthur Scherbius develops the Enigma machine as a means of keeping those business transactions secure. It works by generating an electric current when a letter key is pressed. A number of moving mechanical parts then scramble the path of the current, producing a different letter each time the key is pressed. The Enigma machine is about to become the German Army's most powerful code-making weapon in World War II.
Let's say you've typed in a secret message, "Attack at dawn," into the Enigma machine, and you get this strange sequence of letters and numbers out and you send it to your Nazi companion. Well, now the British codebreakers come along and try and decode that message. How are they going to do it? Well, one of the answers could be by finding statistical anomalies in the actual text that allows them to figure out what the original letters were. Here's a modern paper that talks about one technique that could be used to break the Enigma cipher. Now, while this lecture won't go through the exact techniques used by the Polish and the British cryptanalysts, this repeating sequences goal is one method you might use to help break the code. Find all the places in the message where there's a repeated subsequence of at least L characters. We might do this because repetitions in the text might match up to repetitions in the original message and help us give more information. By correlating the two, maybe, just maybe, we can break the Enigma cipher. So, in terms of actually performing this, let's look for repeated subsequences of at least L characters, taking this example. So here's our secret message, and let's say we're looking for repeated characters, at least 7 of them in a row. So I'm going to run this program on a terminal that I created earlier, and here's the output. I've set up the program so if you type in the name of the program followed by space and then a number, that's the length of the repeats you're looking for. After that, we have some syntax that tells the program, in what am I going to look for these repeats? And it's a file in this case, called test1.txt. Let's look at the output. There are 32 letters in the sequence in total, and we're looking for repeats of at least 7 in length. The output from this program that we prepared earlier is as follows. It tells you that at index 0, there's at the very start of the string, there's already a repeat. It's a repeat of the substring fat.rat. Where else does this substring appear? Well, it appears at the end over there in position 21. You can see at the very end of the string we have fat.rat again, that's 7 characters in length. Likewise, at index 1, we have this string at.rat. that appears at position 25, and then at.eat. appears at position 5 and at position 17, giving us a total of 3 repeated sequences and the locations at which they appear. Okay, so how would we actually go about writing a program that does this? Well, here's an example of an algorithm. This is written in pseudocode, hopefully a style that many of you have seen before. It's a plain language description of the algorithm that we're going to undertake. And so we're going to take a very quick look at this before continuing the next class. So let's call this method 0, a method for finding repeats in a string. Well, first thing do, read in the sequence. So if you have a text file that has, I don't know, some text, and we've got to get that in the program. Once that's in your program, we're going to have a series of nested loops. So from this, there's going to be a bit of reading off the screen. If I just read it out, it doesn't make it very clear. We're going to check some letters, see what's at every position, compare all the characters that are of the length of the repeats you need to see. This sounds pretty vague and hard to understand. Just saying it out loud doesn't make much sense. So the way we're actually going to try and understand this algorithm is by actually writing out the individual steps of the algorithm on a real-life string and seeing how it functions, because this reading out loud method isn't very effective. So let's go back to our sequence. So we have our string over here, and we have our outermost loop. Our outermost loop is going to run through all the letters until we get close to the end. Why might we stop before we get all the way to the end? is there going to be a substring of length 7 starting at the letter R at the very end? Close. The answer from, sorry, Yara. I'll need to work a couple of times. I'm not fantastic at getting it the first time, but we'll get there. So Yara said, is the reason why we don't go all the way to the end because of the nested loop? Yes, in a way, but why is the nested loop relevant? What's the broader picture here about why our outermost loop is not going all the way to the end? Yes.
We start at the end, like to search for the first letter of a substring. It would be like the substring would be just overflow, kind of like the end of the substring would be like on the just overflow.
Yeah. What was your name?
Xingjian.
Xingjiang. I'll get that one too. Take me a bit of time. Yes, so Xingjiang, I'm butchering the name, but forgive me for the moment, was correct. The reason why we don't go all the way to the end is we're looking for substrings of at least 7 letters long. And you can't go 7 letters past the 4th last letter of the string. If we're already on the 4th last letter and we're looking for 7 letters forward, we'll go the 3rd last, the 2nd last, the last, and then we can't go any further. So when we were looking at our for I, let me draw this on so that you can all see it. Oh. If our outermost loop was going from I equals 0 to n minus m, this ensures that we don't go off the edge. Ooh. Okay, so that explains at least the bounds of our outer loop. What about our inner loop? How far should we go with our inner loop? Yeah, anyone in the audience? Liam, let's use that. Where's my little fun thing? Okay, and you'll have to speak loud because it's not going to come through the room system. This will just go for Zoom. Speak really loud.
For the inner loop, we would want to just go to the end of the length of the string. For the inner loop, we'd want to go to the end of the length of the string.
Do we want to go all the way to the end of the string?
Just up until the outer loop reaches, oh no, sorry, only until the outer loop reaches 7 minus the end of the length of the string.
So we're going to have the same problem as we did before. We're going to want to go up until the point at which we can find a substring. Yes, Liam.
Waiter on Zoom says from the length of the substring to the length of the string minus the length of the substring.
You need to speak into that.
Right. From the length of the substring to the length of the string minus the length of the substring.
Yeah, so it's quite clear at this point that we're not going to go all the way to the end in either case because we'll have this same overflow issue. And we will get a hopefully more efficient way of managing all these microphones set up, but bit of an experiment. Okay, so that's echoing. Let's take the example at the initialization. Oh, actually, we are just about out of time. So I think we'll cap it there and go through a full run through of how this algorithm functions and how it progresses along at the start of next lecture. And with that, thank you very much, and I will catch you tomorrow for the next lecture of Foundations of Algorithms.